Well, hello there. This is Dr. Dell, and this is going to be a video on what we call Pythagorean triples. And the idea is it possible that you could show that there's an infinite number of Pythagorean triples? Now, Pythagorean triple are three numbers, A, B, and C, which are the sides of a right triangle. And we know from Pythagorean theorem then that A squared plus B squared equals C squared. And for a Pythagorean triple, we want A, B, and C to all be whole numbers. And are there an infinite number of such things? And so what you might be doing is you might be reading a book and it may come up and say, here's a theorem. For any number k, that's a whole number, 2k plus 1, comma, 2k times k plus 1, comma, 2k times k plus 1 plus 1, those three numbers consist of a Pythagorean triple. Now that's the theorem. And you might look at that and go, well, gee, that's interesting. I don't know where it came from. And in fact, I'm going to talk to you later on this video about where this came from. That's really the point of the video more than anything. Now, let's just take some examples. If k is 1, then if you plug 1 in for k up here, you get 2k plus 1 is 3. 2k times k plus 1 will be 2 times 1 times 2, which is 4. And then the next one here is always 1 more than the previous one, so that's 5. 2k times k plus 1 was the previous one, and add 1. Now what if k is 2? Well, then you get 2k plus 1 is 5. 2k times k plus 1, you can figure it out as 12, and then 13. What about k equal 3? 7, 24, and 25. Now, you can, on your calculator, you should take your calculator and verify that these really are triples. In other words, is 7 squared plus 24 squared actually equal to 25 squared? And indeed it is. What if k is 4? Well, you get 9, 40, and 41. Now, this works for any k, so let's take a larger k, 37. Well, then you get 75, 28, 12, and 28, 13. And you can check with your calculator. Now, what you see is that there's an infinite number of k's, right? 1, 2, 3, 4, 5 forever. And so there's an infinite number of Pythagorean triples. And here they are. Now, this does not mean this is all the Pythagorean triples. There are many more, but this is an example of how you could generate an infinite number of them. Now, when you got a theorem, oftentimes what you'll want to do to make sure if you see if you even believe it, it might start out it's a speculation. You say, well, I think this might be true. And you put in some samples like I did, and it's always true. Well, how do you prove it? Well, you got to prove what? 2k plus 1 squared plus 2k times k plus 1 squared is equal, that's what you got to prove, 2k times k plus 1 plus 1, quantity squared. Now, it turns out this proof of this theorem is actually quite simple. It's just algebra. You can just square over here on both sides. You square this all out, square this all out, and you'll see they're equal. And so the proof is very, very easy. The problem, really, or the question might be, where the heck did this come from? Where did somebody come up with the idea that these would be Pythagorean triples? Now, that's the real question. And often in mathematics, you'll come across a theorem like this, it'll make a statement. And you'll understand the statement. You can apply it to examples. That's the whole point of the statement of this theorem, is to be able to generate Pythagorean triples. And there'll be a proof. Sometimes the proof is easy, sometimes it's hard. In this case, the proof would be very easy. But a bigger question is, where did it come from? And of course, I've given you no hints on that. Now, I'll tell you, I figured this out today and yesterday because I was reading a wonderful book called Fermat's Enigma, and it had something in it I'd never seen before, and it led me to this theorem. I created this theorem myself now recently. And you might say, well, where did you get the idea to do that? Did you just pull those numbers out of thin air? What gave you the idea? Now, I'm going to show you the idea, and that's what this video is really all about. So to do that, I'm going to show you how I got it. Okay, now the question is, as I said, is where did I come up with this idea? Where did I get this from? Well, I was reading this wonderful book called Fermat's, F-E-R-M-A-T, Enigma. I highly recommend it to you. It's a wonderful book if you want to learn about how mathematics was developed historically and all the people involved, and it culminated in the proof of Fermat's theorem by Andrew Wiles in the late 20th century. But in any event, in the book, one of the appendices had the following thing. It said the Pythagoreans themselves, this is now over 2,000 years ago, wanted to prove there was an infinite number of Pythagorean triples. So here's what they did. They started out and they started looking at squares, because after all, that's what they're interested in. And so you can write this down. You might want to be taking notes as you do this, and so on. And they know that they want to be able to add up three squares here, a squared, b squared, and equals c squared. Well, you might take a look at that and see, does this give you any ideas? Well, it didn't give me any ideas, but then they came up with another idea. So let's look at the difference between them. So down here you've got 2 squared minus 1 squared is 3. And here you got 3 squared minus 2 squared, that's 9 minus 4, that's 5. And here you've got 4 squared minus, which is 16 minus 3 squared, which is 9. And 16 minus 9 is 7. Whoa, do you see a pattern here? Stop and look at that and see if you see a pattern. What do you think the next is going to be? Well, 25 squared minus 16 squared is 9. And do you see something here? 3 and 4 is 7. 4 and 5 is 9. What do you guess this would be? Pause the video and think about it. Fill out the rest of these. Pause the video and think about it. Okay. 6 plus 5 is 11. This is 13. This is 15. Now, does that really work? Well, 8 squared is 64 minus 49 squared, that is 15, and so on. Now, take a look at that and see if this gives you any ideas on how to find Pythagorean triples. Well, if this odd number here, if this odd number is a square number, then you're going to have a Pythagorean triple, aren't you? 9 is 3 squared. Right? So you're going to have 3 squared added to 4 squared equals 5 squared. Because remember, 9 was the difference in these two. So this is going to give you 3 squared plus 4 squared equals 9 equals 5 squared. Because 9 was the difference between these. You took 5 squared minus 4 squared to get 9. Do you see that? Stop and think about that. Now, do you see any other Pythagorean triples here? We got one. We got the 3, 4, 5 one that everybody knows about. Well, these odd numbers here are not squares, so that doesn't work, that doesn't work. But what if you go on out, and later on you get out here and you get to 25? Now that would be 12 squared and 13 squared, right? 12 plus 13 is 25. 5 squared, there you have a Pythagorean triple. 5 squared plus 12 squared equals 13 squared. So what you want to do is you want to look at this list and you want to find the odd numbers that are perfect squares. And are there a lot of them? Well, yeah, there are a lot of them, clearly. Let's see, what would be the next one? Well, this was 3 squared, this was 5 squared. These are all odd numbers, you notice. So what's the next odd number that would be squared? Well, it'd be 7 squared, wouldn't it, if you think about that a little bit? So you're going to go out here and you're going to have 49. Now, if you think about it, you divide that in 2, that'd be 24 and 25. And that's 7 squared. This is, of course, 24 squared, 25 squared. And there you have 7 squared plus 24 squared equals 25 squared. So there's the next one. And that goes on and on and on. Now, the general thing you would have, what would be the general one you would have out here? If you have got down here an odd number, what do you got up above here? Well, you're going to have n squared and n plus 1 squared. Because don't you see 6 plus 7 is 13, n plus 1 is 2n plus 1. So that would be the general term out there. But you're really interested now in the ones where this is itself a square number. Now, think about it, and you need to be pausing the video and trying to think ahead as I do this. Okay, now what we want to do is, we've learned now that the general term would be n squared, n plus 1 squared, and then the difference is 2n plus 1. You just multiply out n plus 1 squared, subtract n squared, you get 2n plus 1. But we are interested in the times when this thing is a square. So we want this to be 2k plus 1 squared. That's what we want that to be, because 2k plus 1 is an odd number for any k, right? So that's what we're interested in. Now stop and see if from that you can derive where I got those up above. Stop and see if you can do that. And so now don't you see this is now shows you where I got it from. I have n squared, n plus 1 squared, and 2n plus 1. That's the thing I want to do. And I want the 2n plus 1 to be a perfect square of an odd number. So the n then, this 2n plus 1 rather, is going to be 2k plus 1 quantity squared. Well, what's the n? Well, if I work this out over here, the n is 2k times 2k plus 1. So then I end up with, what's my Pythagorean triple? Well, it's 2k plus 1, and then it's 2k times k plus 1, and then it's 2k times k plus 1 plus 1. And that is where I ended up then with this, where I got it from. So it all started with looking at the sequence of Pythagoreans pointing out that if you have an n squared followed by an n plus 1 squared, the difference is 2n plus 1. And if that is a perfect square of an odd number, then you have the answer. So that's where it came from. Now the trick in math a lot of times is you'll see a theorem proven and you have no idea where it came from, and then you have to really go work and try to figure that out. In my view, you probably don't really understand this theorem until you know where it came from. And of course that's often the challenge when you're studying mathematics, is you'll see a proof and you'll say, my goodness, what did they ever figure that out? Well, usually they've done something like this. They've done a lot of background work leading up to it, and a lot of times that's hidden. The great mathematician Gauss used to say that he never liked to show the scaffolding. What I just showed you here was where we came up with this idea. Where did we come up with these? Well, I showed you where this came from in this example. You might have to watch this video. You have to take notes and think about it, and once you understand it, you'll get an idea. And this is what you're going to have to go through as you learn math, if you're interested, if you're learning math like a mathematician does. This is the kind of thing you learn to go through then. Dr. Dell, I'll see you on another video.